Hello pre-calc people. So in this video we're going to derive the concept of the derivative, and it's going to come from what we talked about previously, a limit, because the limit is sort of the connecting feature in the two branches of calculus. So we're going to start off with a friend from algebra called the average rate of change, otherwise known as slope, rise over run. My own abbreviation for that is AROC, average rate of change. The average rate of change, again, is the rise over the run. So algebraically, we know that as the difference in the y values over the difference in your x values, or slope. Graphically, what does that mean? Well, here's 2 points, so this would be x1, y1, and this would be x2, y2, and finding the average rate of change between them would be basically finding a secant line, the slope of a secant line. Slope of a secant line. Numerically, if we were going to find the displacement, which is the slope from x equals 1.01 to x equals 1 or vice versa, we would go, okay, so f of 1.01 minus f of 1 over 1.01 minus 1, and we would then work this out. And to be perfectly honest, not really concerned with this example, but I'm going to do it anyway. So we would get on top, let's see, 1 plus 1. We would get negative 0.9799 divided by 0.01, and that would give us negative 97.99. That would be your average rate of change. It's your slope, as we traditionally would find in an algebra class. Well, what if we took one of these points and we had it approach the other point to the extent where when it approaches that other point, you reach a problem where then the change in the x would become 0. And since you can't divide by 0, we can't actually let x1 equal x2, but we could have x1 approach x2. And thus, we then have what I call the IROC, which is the instantaneous rate of change. What is the instantaneous rate of change? It is the limit as x is approaching. So now let's call this c f of c up here. So it's the limit as x is approaching that other point, not actually at that point, but approaching, because we don't want to divide by 0. So we've turned our average rate of change into an instantaneous rate of change. Graphically, what does that mean? It means you have now a tangent line. For all intensive purposes, if you make the delta x incredibly small, which is what we want. So the IROC, the instantaneous rate of change, is the slope of a tangent line, that's graphically, which numerically is going to become what we call the derivative of a function at a point. It's kind of like as you are driving through an intersection, and if you drive through a red light, that camera is going to take a picture of you the second you cross that crosswalk in your car, if it's a red light. At that instant, that is the instantaneous rate of change. They aren't gathering your speed, they're gathering a snapshot at that instant that you are at a particular point. So what is the derivative? The derivative of a function, which we denote f prime of x, so you put this little accent here, is the instantaneous rate of change as the one x value approaches the other. These are three ways of saying exactly the same thing. F prime of x is the derivative, is the instantaneous rate of change, is the slope of a tangent line. So let's see how these two can be related as an actual practice, what you would do. So I have an example here. We have some kids playing kickball. Jessie, my daughter, kicks the ball with an initial velocity of 80 feet per second. She's got a strong leg, what can I say? The position of the ball is defined by this equation, and I've provided a graph of it down below, where f of t is in feet and t is in seconds. How could we find the average speed of the ball at t equals 2 seconds? So at t equals 2 seconds, which would be on our graph about here, we're not finding the instantaneous, because again, I can't divide by 0. So what we would do is we would choose a value that is close to 2, but not exactly 2, and we would find the average rate of change around that point. So I'm going to choose something that is 0.01 away from 2. So it's awfully close. And then we would plug those values into our function. So f of 2.1 minus f of 2 is going to give me 0.1584. Down here we have a delta x is 0.01. That is going to give me 15.84 feet per second. Okay, because we have down here, this is seconds, and up here, this is feet. So that is the average rate of change at that point. Could I get a better approximation? Yeah, I could. The way you get a better approximation is I could find a point that's even closer. So I could go 2.001 minus f of 2. And then we would divide that. 2.001 minus 2. That would give me now 0.015984 divided by 0.001, 15.984 feet per second. Notice we're getting closer and closer to a particular value. And the closer I get, in other words, the more you make that interval smaller, around 2, I'm going to get a better approximation of the instantaneous rate of change. If I do the same thing for 4 seconds, which is over here, I can go through the same process. And I should have given myself a little more room. I write bigger on the iPad then. So let's say I did 0.01 again. And if I then divide, so 4.01 minus 4, when you calculate this out, I would have negative 0.4816 divided by 0.01. That's going to give me negative 48.16. And again, if I want to get even closer, I kind of ran out of room, so I'm not going to do that second part. Actually, I can do it up here. Let's say I wanted to get closer. So again, I would choose an even smaller interval. And here's f of 4 divided by 4.001 minus 4. This one, in the end, I'm just going to, since I'm running out of room, just tell you that will come out to be negative 48.06. So you can see, again, I'm getting closer and closer to what we might think is the limiting value, but we're just finding that's just an average rate of change. So that's between two different points. What we want to do is find the actual instantaneous rate of change. We want to know what is the speed exactly when time is at 2 seconds. What is the speed of the ball? So what we do is we're going to take the limit as t approaches 2. So f of t minus f of 2 over t minus 2. Now obviously I can't just plug in 2 because I would be dividing by 0. So we're going to write out what is f of t. F of t is our equation, negative 16t squared plus 80t minus f of 2. So plugging in 2 into the equation, f of 2 turns out to be 96, and I divide that by t minus 2. And again, I should have, so this is just plugging it in. I'm still taking the limit as t approaches 2. Now I can't just plug in 2, but what I can do is simplify this like we did in the previous lesson. I am going to, oh, I lost a 0. Sorry, this was 80t. 80t, sorry about that. Every single one of those terms has a common factor of 16. So I'm going to pull out negative 16. That leaves me with t squared minus 5t plus 6. This is still over t minus 2. And again, we're still taking a limit, but now I can start to simplify this. So on top, I still have the negative 16. I can factor this into t minus 2, t plus 3 over t minus 2. So you can see that this factor now cancels, which is what we want. And again, it's going to be, this is like magic. It's always going to work this way. Something will cancel. So I am now free to go ahead and take my limit. What am I taking the limit of? Negative 16 t plus 3. So when I plug in 2, because that's now a nice function with no discontinuities, it's just the equation of a line, I'm going to end up with 16 feet per second. Oh, that's, you know what, that's because you're like, wait, what? This was a t minus. Somehow I factored that. I said that wrong. This was t minus 3. Sorry about that. T minus 3, t minus 3. So when I plug in 2, I get negative 16 times a negative 1. Now look at this. So this was the actual, if I go to where t equals 2 and I draw a tangent line, the slope of that tangent line, if I were to graph it very accurately, that means I should probably graph it even steeper, is going to be 16. And look at where we had up above f of 2.01, f of 2.001. As we got closer and closer to 2, we were approaching 16. So that is the actual instantaneous speed of the ball at that second, which we couldn't actually calculate as a slope because you would be dividing by 0. Now let's see what happens if we do the same process for at t equals 4 seconds. So we have to take the limit as t is approaching 4, and it's going to be f of 4 minus f of 2. It's still basically your slope formula. And then t minus 4 is, oh, this, I'm sorry, I just took a little vacation in my brain. This should be f of t minus f of 4. So it's your rise over your run. It's the limit of your average rate of change. When we then plug things in, we have the limit as t approaches 4. So f of t is our original function, negative 16t squared plus 80t minus whatever f of 4 is, which turns out it is 64 over t minus 4. And just like before, we can simplify that rational equation by pulling out a negative 16, and that leaves us with now t squared minus 5t plus 4 all over t minus 4 And once again, we can factor this. So negative 16, this will give me t minus 4 times t minus 1, I believe, over t minus 4. Again, here comes the magic. These will cancel out, which frees me up to just plug in t equals 4. So negative 16 times 3 is a negative 48 feet per second, which is the instantaneous rate of change at t equals 4, if I draw that tangent line. So a couple things I want to point out. Notice that the green slope is positive, it's a positive slope, and the derivative, which is what we just found, the limit of the average rate of change is your instantaneous rate of change, and that equaled a positive 16 feet per second. At t equals 4, notice our slope is negative. So the limit of that average rate of change was a negative 48 feet per second, which corresponds to the slope of that tangent line. So what we just did was we showed that the limit of the average rate of change actually equals the instantaneous rate of change. In other words, the derivative at a point, which is the slope of a tangent line. And so now we're going to look at two forms of that, because remember, the derivative is equivalent to the instantaneous rate of change. The instantaneous rate of change is the limit of the average rate of change, which is just slope, just algebra. All right, so what we did before was we basically did this box. So we looked at, as we were approaching f of 2 or f of 4, you have here the average rate of change, and we took the limit as x was approaching that particular point. That is what we would call f prime of c. So we found f prime of 2 to be 16, and we found f prime of 4 to be a negative 48 feet per second. Okay, now the idea there is you have two separate points. The x value is approaching that c value. We can rewrite this equation so that we don't have to look at two separate points, we only have the one. So what we're going to do is we are going to substitute where you see x minus c, we're going to just substitute in h. So that is going to replace the x minus c. That means that we are just approaching the difference between x and c. We want that difference to be 0 between those 2 points. And again, we can't divide by 0, so that's why we take a limit as h approaches 0. H now represents your delta x, the change from one point to the next. So in the y values, what that means is it's f of x plus h minus f of x. So that you're still the difference, but it's still average rate of change. It's just a different notation. So let's see how this plays out. We're going to look at this graph over here, and we're going to use the h form, which is this one, to find the derivative, a generic derivative, because if you want to find the slope at a certain point, that's nice, but then that means you have to go through that process for every single point. What if we could come up with a formula so that if I wanted to know the slope at any point on the graph, I could then use that formula. So this is what we're going to do with the h form. So I have the graph here, x squared minus 4x, and we are going to find a generic formula for the slope at any point on this graph. So this is how this works. We know that f prime of x is going to equal the limit as h goes to 0, so that's like saying as my two x values are approaching each other, f of x plus h is going to be substituting. So we want to find f of x plus h. That means I substitute wherever I see an x, I'm going to substitute in x plus h. So in my equation, x squared minus 4x, I'm going to have x plus h squared minus 4 times, instead of just x, it'll be x plus h. Then I'm going to subtract, so that's your f of x plus h, minus just f of x. What is f of x? It's x squared minus 4x. And all of that now is going to get divided by h, which I'm just going to kind of put off there to the side so I save some room. So what we have to do is FOIL, expand, combine like terms. Again, there's going to be some magic happening here. So we're still taking the limit as h approaches 0. I'm going to FOIL out x plus h squared, so that's going to be x squared plus 2xh plus h squared. I'm going to distribute this negative 4, so negative 4x minus 4h. Then distribute this negative, so minus x squared plus 4x. And again, all of that is going to get divided by h. So what happens next is, first let's simplify our numerator, because a bunch of things are going to cancel out. So we have this x squared will cancel with this x squared. I have minus 4x will cancel with positive 4x. And that's it. Okay, so let's look at what we have left. What you have left, and it's always going to be this way, has an h in every single term. So I'm going to factor out that h on top, so that I just have 2x plus h minus 4 all over h. So these two will cancel. Now what is left? I have no more denominator. That's your goal. Your denominator is gone, just like we did in the previous problems, so that I don't have a problem child. I'm not going to be dividing by 0. So I am now free to just plug in h equals 0 as a limit. When I do that, I get 2 times 0. Sorry, I just really blew it there. That was silly of me. I'm going to get 2 times x, because remember, it's as h goes to 0. So plus 0 minus 4. This simplifies to 2x minus 4. That is your formula for finding the derivative of this function, x squared minus 4x, at any point. So now if I want to find, rather than going through the whole process for every individual point, if I want to know what is f prime of 1, so on our graph, 1 is, where is 1? I'm looking at my scale and it's kind of hard to see my scale. 1 is right here, I believe, because that's 2 and that's 4. So here would be 1. Let's see, what is f prime of 1? Well, I plug it into my 2x minus 4. 2 minus 4 is a negative 2. Oh, that kind of matches. That looks like a negative slope. Let's find another point. What is f prime of, let's choose another place. Let's do f prime of 3. So 3 is here. That would be the slope at f prime of 3. We plug in 2 times 3 is 6. 6 minus 4 is 2. That would be the slope of that tangent line. Now, here's what we really like. Let's find f prime of 2. Notice that 2 is where you have your vertex here, your max or your min. If I plug in 2, I get 4 minus 4. Voila. This is really important. This is an easy way to find all your max and mins by just taking the derivative and setting it equal to 0, because the slope of any max or min is going to be 0. Notice that f prime of 2 is 0. So we'll be utilizing that fact later on. Okay, so let's do a few more examples just to kind of get used to this. So we're going to find the first derivative of each function. Next year you'll be finding first and second and third derivatives, but that's all good. So the first derivative, and we're going to use our H form. So this is just a linear equation. Think about a linear equation. What is the slope of a linear equation? Does it ever change? Let's see. So we're going to find f prime of x using the H form. So that's limit as h goes to 0. So we first are going to plug in, wherever you see an x, we're going to plug in x plus h. So I have negative 4 times x plus h plus 3, that's the first part, minus just f of x, which is negative 4x plus 3, all divided by h. All right, let's simplify this out. So use a different color. So we have here now the limit as h is approaching 0. So we have to simplify. So we're going to do a lot of foiling, or not, in this case we don't have to FOIL, but we do have to distribute. So I'm going to have a negative 4x minus 4h plus 3, and then distribute the negative. So this becomes positive 4x minus 3, all of that over h. So we simplify. Notice that you have a negative 4x and a 4x goes away. 3 goes away with negative 3. And I'm left with the limit as h approaches 0 of negative 4h over h. And of course, now our h's go away. So your answer, it's just that constant, is negative 4. Which makes sense, because if you have an equation of a line, negative 4x plus 3, it has a constant rate of change. It's always going to be negative 4. So yes, this was a long way to find the slope of a linear equation, but I'm just trying to show you that this form of a derivative will find the slope at any point. And if it happens to be a line, the slope will be whatever the slope of that line is. Of course, you're crazy if you go through that process ever again on a linear equation, but I wanted to make that point. All right, so let's go back to a quadratic where your slope of the line will change, and let's go back and use our first form so that you get comfortable with both, because it may ask you to use the H form, or it may ask you to use as x approaches c form. So what did we do before? We did, I should actually emphasize again, what are we doing? We're finding f prime of x at any point. So we're going to take the limit as x approaches c. So we want that delta x to be 0. And that means I'm going to do f of x. I'll just remind you of what this actually says. So this is going to be f of x minus f of c over x minus c, your average rate of change. So f of x is our negative x squared plus 6x plus 7 minus f of c. Well, f of c is just going to be substituting a c in for your x term. So I have negative c squared plus 6c plus 7 all over x minus c. All right, let's go through and simplify things. So the limit as x approaches c is going to be, now this is, okay, let me get rid of my negatives. I'll do one step first. So I have a negative x squared. I'm going to kind of put some kind of like terms together. Like these terms are going to get together. These terms I'm going to put together. And these terms I'll put together. So I have negative x squared plus c squared. Then I have plus 6x minus 6c. Then I have plus 7 minus 7, because I'm distributing that negative all the way over there. This is all over x minus c. Okay, so let's kind of simplify this out. I can do a little more magic here. I am going to factor out a negative here, in this first term, this becomes negative x squared minus c squared. And I can factor out a 6 here. So this will become plus 6 x minus c. And you can see that those are going to cancel. And this is all divided by x minus c. So a little reminder is what we have here on top. This is a difference of squares. So I have negative x plus c, x minus c, plus 6x minus c, all divided by x minus c. So I can factor out an x minus c from all my terms, and they are gone. Adios. And what do I have on the bottom here is the limit as x approaches c, negative x plus c plus 6, and nothing on the denominator. So now that I don't have any problem children in the denominator, I'm not going to get 0, I'm not going to be dividing by 0, I can substitute into that equation. Remember, x is approaching c, so I am going to just substitute c in for all my x's, and I get negative c plus c, so that's going to be a negative 2c plus 6. So what, actually I should have written here, we found f prime of c, but you can generalize that. C is just a variable, so really what I have, f prime of x equals negative 2x plus 6. That is a generic formula for the derivative. So this is the slope of any tangent line to the graph. So you just have to plug in that particular value to that particular graph, to f of x. So if I wanted to know what is f prime of 1, I would just plug it into that equation. All right, so it's two different ways to find your slope. Now, you might be saying, dang, that's a lot of work. And I was very nice and I didn't give you any cubics or quartics to figure this out because, frankly, I wouldn't have enough space. So, of course, there's going to be a shortcut. So as I said before, we are just getting a very generic overview. You're going to be doing some grunt work in calculus to kind of show the derivation of where these shortcuts come from, like what we just did in that previous page. Just like we did with limits, you won't get to immediately do the top heavy, bottom heavy limits. You're going to have to do some other calculations, but I'm trying to just get at the gist of what we're doing. So we do have a shortcut for derivatives because that was a lot of work that we just did doing the limit of the average rate of change. And it did give me then a formula. So we would rather come up with a shortcut, but there are some preconditions that have to exist. So if I have a function, if f of x equals, so let's say you have a scalar multiple coefficient and it's a power function, x to the n. And now this is important, f of x has to be continuous wherever you're finding the derivative. You can't find the derivative at a point that does not exist, but you also, it has to be a smooth curve. So it can have no, what we call cusps. A cusp looks like this. It can't have any sharp points like that. It has to be a nice smooth curve. And if that's what you have, like any polynomial is a nice smooth curve. Although I just drew sine or cosine, which are also smooth curves. Then the derivative, f prime of x, can be found by doing what we call the power rule. So your coefficient a just kind of gets carried along. N is going to travel downstairs. And so you're going to have n times x to the n minus 1. In other words, the slope at any point is always going to be 1 degree less than whatever your function was. And you saw that. We did the linear equation, negative 4x plus something. And what was the result? The derivative was just a constant, negative 4, because that's your slope. if you had a quadratic, notice, go back and look, all our slopes were linear equations. The slope is always going to be 1 degree less. So let's do a quick little example here. If I gave you f of x is, I'm going to make this a difficult one, 3x to the 4th minus 2 over x, notice I can rewrite that as f of x equals 3x to the 4th minus 2 times x to the negative 1. So what is my derivative? My derivative, f prime of x, 4 is going to come down and get multiplied against the 3. So that's going to give me 12. X, 4 minus 1 is 3. And then now the 2, this negative 1 is going to travel down in front. So I get a positive 2 now, right? And then x, so negative 1 minus 1, this becomes negative 2. That would be your derivative, without having to go through that whole limit of the average rate of change. It's like, whew, so much easier. Okay. But I will say that concept of the limit of the average rate of change is huge, and the AP test will really try and drill that into you. So it's a really important concept, even though you do have this nice shortcut just to find a derivative. All right, the sum rule. Well, what if I have two functions? So if I have f of x equals, say, h of x plus g of x, I'm making stuff up. All right, so it happens to equal the sum of two different functions. It's kind of what I just did in that previous example. That was kind of silly. That's okay. Then f prime of x is going to equal h prime of x plus g prime of x. You can just take each term's derivative and still add or subtract. So this works, you know, because subtraction is really just adding the opposite, so it works. However, dun, 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 big problem, this does not work for products. So if f of x equaled g of x times h of x, for instance, if I had, oh my goodness, 3x squared times x squared plus 1, f prime of x does not, I wish I had read here, does not equal g prime of x, h prime of x. You are going to get something called the product rule and chain rule and all these other fancy rules later on. So do not do this. It only works for addition and subtraction, where you can take the derivative of each term separately. All right, let's do a little practice. So what do we have here? F of x equals 5. It's a constant function. Well, what is the slope of a constant function? Think about that, right? Sometimes it helps to even kind of graph it. That's what, say, x equals 5. Well, you can also write this as x to the 0. And if I use my power rule, the 0 comes down in front, and you find that the derivative of a constant is going to be 0. Oh, silly me, that's over here. Okay. Dun, 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 dun. So I wouldn't usually write the x to the 0, but that's just emphasizing you can do that to see that that's why your derivative would be 0. But again, here is a constant function. What is the slope of a constant function? Because that's what a derivative is a slope. The slope is 0. G of x equals 6x. Well, that's a linear function. What's the slope of that line? It's 6. But if we do the power rule, again, the 1 is going to come down. 6 times 1 times x to the 0. And voila, you get g prime of x is 6. All right, let's get a little more difficult here. So now we have a sum of two, or difference of two functions. So my derivative, I guess I stopped writing it over here, is going to be, so the 3 will come down. I'm going to write it all out this time. 12 times 3, x to the 3 minus 1, minus, now here I recommend if you have a radical, write it as a fractional power. So that's minus 3x to the 1/2. So we bring down the 1/2, which gives me 3/2. And 1/2 minus 1 is going to be negative 1/2. So I can simplify this. This is going to equal 36x squared minus 3, and we tend not to leave negative exponents, so the 2 is down here, and now the square root of x is going to join it. That would be the simplified version of that derivative. Okay, and you'll get to use that radical. You'll notice a lot of times the derivative of square root of x is going to be 1/2 with the square root of x in the denominator. All right, what if, again, here I have another fractional power, so m prime of x, so this will come down, so we'll have 9 times 2/3 times x to the 2/3 minus 1, getting kind of crunched here, so I can simplify this to 6, and then we're going to have 2/3 minus 1 is always going to then be negative 1/3. So I would write this final answer as 6 over x to the 1/3, or cubed root of x, however you want to write it. I don't care. All right, now we have 1 over x squared, which I would recommend you write this, because you can't just take the derivative in the denominator, so I would write this as x to the negative 2. So v prime of x is going to equal negative 2 x to the negative 3, because you're subtracting 1. And since we don't like negative exponents, it seems kind of sad, but we don't. We write it like that. Okay, now I'm going to throw a little loop at you. We have here sine. It's like sine's not a power function. How would I find the slope of sine x? So we're going to kind of derive it just for fun. All right, so let's take a look. What does our sine graph look like? Remember, it starts on the sinusoidal, goes high, goes low, comes back on the sinusoidal. So there's your y equals sine x graph. And we're trying to be able to find the slope at any particular point. And so to do that, actually, so let's use the h form to see what we can come up with. I might be going a little bit beyond the expectations here, but we're going to try it. So I'm going to start off with the limit as h approaches 0. So remember, in this form, you replace x with x plus h minus sine x all over h. And, sorry, don't mean to stress you out here, but do you remember your I don't even remember what they're called, composite functions? We can expand sine x plus h as sine x cosine h plus cosine x sine h, and then we have minus sine x still, and this is going to all be over h. Okay, so what can we do to this? Well, I'm going to rearrange, do a little magic here and rearrange a few terms. So I have here the limit as h approaches 0. I am going to take these two terms and put them together so that I have sine x, which I can factor out, cosine h minus 1 all over h, plus here I'm going to have cosine x times sine h over h. Okay, I realize I'm getting a little bit ahead because there's some things here you don't realize yet, but sine h over h, you're going to learn about something called the squeeze theorem later on, that this limit right here is going to approach 1. And then the limit here, cosine h minus 1 over h, that limit, when you do your squeeze theorem later, and you'll learn some other limit tricks, is going to approach 0. So what I end up with as h is approaching 0, this whole term then, the first term turns to 0, and my answer is cosine x. The derivative of sine is cosine. And if you don't believe me, I'm going to put in here a cosine graph. So remember, your cosine graph looks like that. So let's look at what happens. The slope at 0 of sine, notice if I made a little tangent line, the slope of that line should be 1 because the value at 0 of cosine is 1. What happens at pi over 2? Remember, at pi over 2, your slope here, that's a maximum, is going to be 0. Well, pi over 2 on cosine is 0. So every value of cosine gives you the slope of a tangent line to your sine graph. And I realize that was kind of going a little bit above and beyond, but it's kind of fun. Just so you know, we can get beyond power functions. And wait, actually, you probably don't get the joke on the calendar about the log cabin. That'll come later.